Hi everyone and welcome. My name is Jessica and I'll be your webinar host today. Today's webinar will be 2 hours long. Our subject matter expert presenter for today is John Ross Cromer. Before I turn the webinar over to him, let's take a moment to review some basics for today's session. First, it is very important that you attend the whole webinar and participate in all polling questions. Your time in this session, as well as your participation in the polls, are monitored for proof of attendance to receive your CE hours. This is required by the accrediting bodies. If you have any questions, please contact your account representative or corporate account manager. When you joined the session today, your line was automatically muted. We do that to cut down on potential background noise and to give you the best opportunity to hear the presentation. If you'd like to ask a question, please open the Questions tab that's located in the control panel. We'll be monitoring questions and either John or I will answer them. Also, John will be asking you polling questions throughout the webinar. He'll explain how to answer them when the time comes. Please note that you will not be able to answer the polling questions in full screen mode. You can minimize the screen to make your answer selection. You will also find a PDF copy of the presentation located under the Handouts tab. Please feel free to download this document so you can review the material that John will be presenting today. Now, since this is a 2-hour webinar, we'll go ahead and take a 10-minute break around 1 p.m. Eastern. And regarding certificates, your certificates for today's webinar will be available in your Rector account by tomorrow afternoon. We'll send you an email notifying you when they're ready to be downloaded. Please note this information regarding the accreditations for this webinar. If you have any questions, please contact your account representative or corporate account manager. Thank you for your attendance and participation in this session. As I said today, our subject matter expert and presenter is John Ross Cromer. At this time, I'll pass control of the webinar over to him to get started.
All right, thank you, Jessica. Good afternoon, everyone on the East Coast, or you're getting there, all other time zones. Today we're going to learn about National Electric Code. If you have follow-up questions from this program, feel free to send me an email. I'm actually starting a new job at a lithium iron phosphate battery manufacturer tomorrow. So that's the email address in the presentation. I'm also kicking off the chat. I'm sending my alternate email address to the chat room. So if you want a recording of the program or follow-up questions, feel free to contact me. You know, my background is an engineer, mechanical engineer. I took some robotics classes in college, but I really didn't appreciate much, of the nuance between a volt and an amp, other than, hey, we have to make sure we size the things appropriately. That was good enough to get me into control systems engineering job in the oil industry before I took a look at solar about 10 years ago and said, well, that looks, simple enough, for me to figure out. Again, we're matching volts and amps. Only after I got into the industry, experienced as a residential contractor, leading the design and development and hiring electricians to do the electrical scope. Only after I actually made it into the field and started building the systems with my own hands as a contractor did I fully appreciate the value of having an electrical inspector who could just show up on site and, without even knowing anything about solar, evaluate the system head to toe and point out things that either he caught that I missed. So, well, how do you do that? Well, he has a comprehensive understanding of electrical safety, workmanship, and principles. And what National Electric Code tries to do is be a cheat sheet to how electricity works, how it should be sized, so that electricians can design and install the final end of the system in a safe manner. Now, when I got into solar, I mastered all parts of, Section 690 related to solar arrays. But I found that as an engineer without true electrician training background, I was lacking in the understanding of the initial sections of code. So I wrote this program kind of reflecting on kind of the journey of needing to develop comprehensive electrical code knowledge that you would need to, say, pass a master electrician exam. So let's say you're an engineer. In many states, that will allow you to be a master electrician of record if you can pass the master electrician exam. So as engineering managers, you might find yourself, especially with the advent of solar and batteries being pushed into final electrical design, where we're teaching this class today, to give a run through of the initial parts of code. Let's go ahead and get to it. So this will develop your knowledge of balance of system material, how electricity works, all sorts of that today. Right, there we go. So these aren't the real titles to the sections of code. In fact, looks like I got it a little bit out of order. But Article 100 just starts with the basics, definitions, just an easy starting point. From that point on, electrical code kind of follows a natural pattern. Section 2 talks about how power enters the building through power supply. So utility service conductors, and not just how it enters the building from the grid, but from one panel to the next. So, we start with definitions and then we get into supplying power to electric service panels. Section 300 then governs the wiring between the panels. So we talk about, feeders and supplies in section 2, and then all the rules that govern the cables between those sections. By the time we get to section 4, it covers general equipment. And so, just flipping through a code book, rather than having to thumb through every section, you think, well, how advanced is this issue? Is it a general supply issue, conductor sizing? That sort of stuff is in section 2. If it's more about the specifics of a particular cable, its temperature ratings, the type of conduit between the runs, that's in section 3. By the time you get to section 4, you're into more general applications, lighting, kitchens, motors, just general appliances. And beyond that, you get into specialty sections, batteries, solar, grid interconnections. Today, we're going to focus on the first 4 sections of code up to batteries. Next month, we kind of pick up where we left off, getting into the battery, solar, and interconnection sections specifically. But again, if you just start at those special sections, then you kind of lose a comprehensive mastery of code. And that's very limiting, say, in the solar industry, where, often we will put solar on top of the roof or next to the building, but we don't incorporate it in a beautiful manner into our building facades, even though at the end of the day, you might have a expensive building facade that's already being built. Why not combine the projects together? Well, your solar installers just focused on putting solar on the rooftop isn't going to have that comprehensive exposure to building design. And so if we want to drive our building infrastructure, our electrical infrastructure forward, and actually make advanced buildings that store energy and capture energy and do it in a beautiful manner, that's where the engineers and architects really need to get in and understand how to lead the design through that process. Okay, so the first 3 sections of code, the definitions, the wirings, methods, and the power supply and services are in the first 75% of code. All the specialty stuff is just 1/8 of electric code kind of at the end. And so let's we have a long 2 hours ahead of us. Why don't we start by practicing our first polling question? So what I'm going to do is launch a poll, and this will help me understand the audience skill level today. So go ahead and answer this poll. We got to get to about 90% voted before we can move on. So these poll questions don't have to take all day, but let's go ahead and vote. And so far, how things are going is we got about 20% of class who are National Electric Code experts. Feel free to sharpshoot either in chat or through emails because we do keep this class up to date. We want to have stuff for you. However, 70% of the class is saying they either know none of electric code or only sections relevant to my trade. So let us then close that poll and move on to okay, so now we're sharing it. So this is how the class turned out. So we'll pick up speed on those polling questions on the next one. And here we go. Let's keep going. All right. One bizarre thing about National Electric Code is it is not actually like the electric code of the United States of America. It's a private organization and they copyright the material. And so that's where when you're referencing National Electric Code, and I'm even uneasy about giving out handouts of this particular class, but you'll notice as we go along in class, there's like gaps in sentences or sections of the table that are missing. It's not the full picture, and that's because National Electric Code does not allow you to share that full picture. They want you to reference National Electric Code by reference only and keep it kind of closed off in that regard. So that what they're saying is you need to purchase a copy of National Electric Code to have the actual electric code in front of you. That helps them maintain it. And so it is subject to a copyright. Now, sometimes states will have their own code that's their state code, and it's almost a word-to-word verbatim of electric code. But technically, if you're in a chat forum and you're talking about electric code, you're supposed to reference it by the section and reference number in the title, but not spit out electric code on discussion forums, all over the place. That helps kind of rein in the professionals and keep the do-it-yourselfers at bay. Let's talk about some 2020 changes. The ones that I find most interesting is that it's the concept of an exterior disconnect switch for utility personnel to come up to on the outside of the building, and they turn that switch from the on position to the off position, and it shuts down the on-site power systems. So, imagine a panic button, but it's on the outside of the building rather than the inside of the building, and it can turn off all the power to the building. And, not all building professionals have thought that that would be such a good idea because, that means anybody out there can come and turn off power to your building. Also, there was a safety issue because you're taking the power system of the building outside in a readily accessible location. Someone got into that box, they could stick their hand in and electrocute themselves. And that's really a solar installer issue. These exterior disconnect switches need to be locked so that people can't open them up and take a look inside. But this is for fire safety. This is for the firemen to be able to come out on site, turn that switch, and de-energize the building. This is not necessarily the same main disconnect switch as would be on a power system. This is an additional switch that goes outside the building. It might be your main disconnect switch if everything's already outside the building, or it might just be an additional disconnect switch that goes out of the building and then back into the building to where the equipment is. And so this code, it used to be mandated by local jurisdictions, and then the solar industry pushed back and said, actually, the main disconnect switch inside the building right next to the service panel, that's good enough, and so we don't want to do this additional hazard and cost. And many jurisdictions, the tide was kind of turning in that favor, and many jurisdictions were getting rid of their exterior disconnect switch local requirement. And now electric code NEC 2020 comes back and says, well, it's part of national electric code now, so you have to have this exterior switch. And at any rate, once you get above a certain voltage level, the switches have more requirements, but let's just leave that for now. The exterior disconnect switch, commonly a knife switch, is now mandated in electric code. Some additional requirements for powered over Ethernet devices. That's a specialty section, towards the back. One we'll reference in class today is the load calculation charts have finally been updated for LED lighting. And so there's minimum loads that you have to design a building for and a power system for, found in code. Incandescents and LEDs have a 90% difference in energy efficiency. And so these tables have finally kind of been drawn back to say we can design the footprints of buildings to have less energy demand because of the reduction in lighting load. And then we have introduction of requirements for the safe use of electric vehicles as backup power for your batteries, which is kind of interesting. We think of battery inverters and solar inverters for that direction to be able to charge from the grid and then discharge from the grid. In our inverter classes, we talk about that's a two-way inverter, both the charging and the discharging. A lot of inverters are not two ways, they're one way because it's cheaper, just charging. So like electric vehicle batteries have had less grid restrictions because they've just come from the grid into the battery. But now, customers are wanting to put those batteries to use when they're at home. And so the electric vehicle inverters now are being listed for bidirectionality. It's something the solar industry has already gone through. So very similar requirements. And I expect that the rapid shutdown requirements in solar will soon apply to batteries as well. A little bit advanced. That's the end. That's stuff down the road. Let's kick it off with Article 100. The big thing here is the difference between accessible and readily accessible. And so the main thing is something that's readily accessible has to be approached without climbing or the use of a ladder, whereas accessible is something you can walk up to, but you might have to climb over something to get to. So you can have an accessible box in your attic, but a readily accessible item could not be in the attic. At any rate, this knife switch on the outside of the building needs to be readily accessible. One thing that took me for a spin was utilization equipment. Utilization equipment are appliances. So solar or battery inverters are not utilization equipment. So if you come into any exception for utilization equipment, that does not apply to solar battery banks. AHJ is the authority having jurisdiction. So ultimately, it's your local authority, your local permit office, whether it be the power company or the distribution cooperative or the state or the city inspector. One of those entities is the one that says we are going to mandate national electric code. And so it is actually quite common for a local jurisdiction to not only mandate electric code, but make additional rules or regulations pertinent to their area. So for example, in New York City, with multi-story apartment buildings, they may say the risk is so great that they're going to increase the conduit protection requirements for the local jurisdiction. So I would not just dismiss additional local AHJ rules out of hand. And often if you're trying to do something more advanced with your design, being able to put it into your design and permit beforehand and running it through the permit office can work in your favor. There's Bonding, it's similar to grounding. It's just not connected to ground, but you touch two pieces of metal together, and if they can, conduct electricity, that's considered bonding. And we have to make sure when we're using metal parts that they're bonded. So there's a lot of that in reference to the grounding discussion. Continuous loads and non-continuous loads. The magic number is 3 hours. So if a load is expected to run for 3 hours or more, it's a continuous load. Loads that are non-continuous run for less. More on that later. Here's a term, dead front. It's without live parts being exposed to a person on the operating side. And so what that means is, when you open up the lid to your electric service panel and you look into it, you don't see the wires, you just see the breakers and then this piece of metal that covers it. That's a dead front. Sometimes when you open up a solar breaker box, you just look straight into the terminals and see the wirings. And if I often will get a customer say, well, if I stick my hand in there and touch those things, will I kill myself? And the answer is, yes, you will. And so depending on where, like that readily accessible exterior disconnect switch needs to have a dead front on it, so that if someone, curious opens it up, there's a guard for them. Branch circuits versus feeder circuits. So feeder circuits are power supply circuits. They're dedicated for supplying power, whereas branch circuits are circuits that you're connecting loads to. And so solar and batteries, for that matter, can be connected actually, not just right out by the meter or right by the service panel, but they can be connected to any feeder circuit. They just can't be connected directly to branch circuits. So you can't have the supply and the load sharing the same wires. You have to keep the loads on their own dedicated circuits, then wire up to a service panel, and that dedicated supply line would be called a feeder circuit. We have charge controllers being defined. It's a term for other solar classes. Conduit bodies. So we have conduit or tubing that provides access through a removable cover. And so, when we think of conduit, we think of like PVC conduit or metal EMT conduit. But in fact, there's a wide variety of ways that we can enclose the cables, the actual wires from point A to point B. And so that's all categorized as raceways. And conduit bodies are a kind of raceway. So whether it's a tube or a box or a wire, can trigger a specific term in reference a specific part. Enclosures, so housing, fences, walls surrounding to prevent accidental contact. The good rule of thumb is, your electrical devices need to be, protected and safe and enclosed. Those enclosure requirements ramp up with higher and higher voltages. And so and where the code is going is that manufactured, stamped, listed, assembled parts like the Tesla Powerwall will have different, more lax electrical code requirements than if you decided to build your own battery pack out of listed batteries and put them on a shelf. And so, the general rule with solar and batteries is that this equipment needs to be fully enclosed, or if you're building your own battery bank and you're just putting the batteries on shelves, that area of the root, that area needs to be enclosed. You can't just because an installer is putting a Tesla Powerwall on the wall of their garage does not mean that you can also put a bunch of batteries up on the wall. So there are enclosure requirements to prevent accidental contact. And if you're inspecting something and you're concerned about accidental contact, you would want a dead front on your boxes. Fittings are the names for all the little metal pieces that connect the conduit and boxes together. So whether it's the connector that goes between the conduit and the box, or the coupling that connects two pieces of conduit together, or the lock nut or bushing that can help the connectors fit into the boxes, all of that is grouped into a piece called fitting. And now we're going to get to next poll question. So let's go ahead and answer this one. What is the difference between an arc fault and a ground fault? We're about to look at some examples, get some pictures into the presentation. But let's go ahead and answer this poll question. What's the difference between an arc fault and a ground fault? So we haven't covered it yet, so you're going to have to guess on this one. An arc fault occurs in a gap between within a conductor, and so that would be like if you chop the wire in half and then you hold the two ends up to each other. An arc fault occurs between two powered conductors, and so let's say you have a leg 1 and leg 2, and then we have a ground fault occurs between powered conductors and grounded conductors. So there's actually a grounded conductor, could be your equipment ground conductor. Also your neutral wire would be considered a grounded conductor, or all of the above. So let's get up to a 90% participation poll. That's really why we do these polls, is so that you're documenting your participation throughout the program. So we need a 90% to keep going. So we're almost there. We're at 85%. We need another person or two to vote, and then we'll close. One more vote. Come on, guys, get out and vote. All right. So we're going to close that and share. This is all of the above question. So let's take a look at some arc faulting. So arc faulting can occur within the circuit itself without any pathway to ground. And so if a connector is loose and it's not making a tight connection, you can get an arc fault. If you over crimp a connector or under crimp, if you over crimp and then you bust some threadings off of the copper wire, and then now you have little copper ends that are cut, and there's a little gap of air between that and the metal connector, which should be a more solid contact, but it's not. You can get a little arc current between that. And so in the solar world, we have this black connector on the right called an MC4 connector. And if that connector is not plugged in with a solid snap, or if they messed up the insides of the connector where it's supposed to be a male and female metal piece, but if they look very similar. So they accidentally crimp like a female to female, and they try to shove the connector in, and some of these construction guys are so strong they can make it fit, sort of, and you could get an arc fault within this MC4 connector. So arc faults occur, within the line. They can also occur to describe a fault between two powered phases. So if you have two powered phases that are of different voltages, whether it's a 48 volt circuit and a 12 volt circuit, or a 120 volt circuit and the oppositely phased 120 volt circuit, arc fault can occur between those two as well. A ground fault occurs between a powered conductor that's faulting, into ground. And so an arc fault could get dangerous, a lot more dangerous if it becomes a ground fault. It used to be back in the solar industry, we didn't worry about arc faults. the arc fault detection is harder and more nuanced. You can imagine, detecting little changes in volatile voltage caused by this tiny connector. That's a lot less dramatic than a ground fault. So arc fault detection has, only come on of late. Now inverters are equipped with arc fault detection, but the inverters 10 years ago were not. So the solar industry 10 years ago had this reputation of being bulletproof, never had an issue, when in reality, some of these arrays might have minor arc faults going on, that are not an issue today, but could be an issue down the road. Yeah, so again, a common one that I have found in the solar industry is these little black connectors. Not just if that ending is not connected with a click, but if these connectors at the bottom are not fully tightened up to secure that cord well within the connector head, that can cause an arc fault. If everything else is perfect on day one, you start the system up and one of the circuits is not checked in, it's probably in one of these connectors. And if the circuit did check in and then all of a sudden a day later it doesn't check in, it's probably an arc fault in one of the connectors that is field made between the array and the inverter. So ground faults are much more dangerous. An arc fault, could find a path to ground and then become a ground fault quite easily. And so this is a rooftop we did in West Virginia, and as you can tell, the roof fills up with water every single time it rains. The roof elevation was not such that when they installed the drains on the roof, they could put the drains below the roof deck. Instead, in order to adequately seal the penetrations made by the drains, the drain holes all had little levees built up around them. And so, in fact, the rooftop needed to hold, about 2 or 3 inches of water before any of the water made it into the drains. I don't know if on those rooftops the solar array is the smartest idea, because if those connectors are droopy and they droop down onto that roof deck and then they get full up with water, you have metal connecting the solar array to ground, and so just a connector on a roof deck in the rain full of water, can cause a ground fault. So you do have to approach particularly commercial solar very cautiously and have good cable management all the way through. For whatever reason, there's no code that I know of governing pools of water underneath 1,000-volt solar electrical systems, and maybe there should be, but that is to drive home the fact that when you have electricity faulting to ground, that is called a ground fault. That can be what burns the hole in the roof and causes the building to burn down. So, workmanship is important. And in fact, most solar fires in the industry that have occurred and burned buildings down because of it have been on commercial rooftops. So just pay particularly attention to water issues on the roof is my recommendation. So anyway, let's diagnose this problem up on screen and try to determine if it's an arc fault or it's a ground fault. Because that'll help us kind of figure out what went on here. So here we have the inside of an inverter block, and we got leg 1, leg 2, and neutral. So this is going to be on, and we can see down here it says AC grid. So this is the grid side coming in from the grid. So it's probably not a DC side solar array issue. And so, obviously we got some heat going on here. So what caused this from happening? What we see is this is an arc fault, because the neutral's the ground connection, and what we got is some arcing between leg 1 and leg 2 here, and so that is not a ground fault contained somewhere else in the system that might be connecting to ground and pulling electricity from power into the neutral along with it, or something like that. These two wires plugged into this terminal block touched, and that was causing arcing between them, and it burned up that terminal block. And so the question is, well, why wouldn't that trip the breaker? So this inverter was on a breaker, but the electrical issue is going on. Well, it can or it couldn't. We have to go and look at how breakers work, and if that breaker did not have, and these arc fault detecting breakers are a little more advanced than just a breaker you put on a solar inverter for. And so it's like, well, why did the arc fault detection in this inverter not trigger when an arc fault was occurring? And the answer is, well, because their arc fault detection's on the DC side, it's not on the AC side. So, we had an AC arc fault that wasn't on an arc fault breaker, and it's not being detected by the arc fault detection in the solar inverter. This is a workmanship issue. So arc faults, can be difficult to detect. They can continue without much interruption to the service if it's a minor arc fault. So you might get some kind of phantom errors that you can't diagnose particularly well without any breakers tripping. That can be an arc fault, and they can precede ground faults. So in this case, we were able to look at the conductor and measure it. And here we have the instruction manual calling for stripping to 1/3 of an inch. And so the instruction manuals say strip to 1/3 of an inch, and the installer stripped to a little over about 5/8 of an inch. So they took off nearly 2/3 as much material as what the 2/3 additional as what the manufacturer was calling for. And because these two wires were stripped too long, when you plug them into that inverter, they get an arc and it burns up the terminal block. So, following the installer's manual instructions all the way down to how much material should be stripped off the cable can be specified for the installer in advance, by a detailed enough designer. So let's talk about ground faults and ground fault breakers and breakers in general. So how does a breaker work? Well, when you put 20 amps of load through a breaker, a standard breaker, if you put more than that through that conductor and allow it to continue uninterrupted, if you overcharge a cable beyond what its ampacity is rated for, it'll start to heat up. And when it heats up, it's gonna smolder. The way that a breaker works is there's this coil inside the breaker that when the electricity begins to heat up, that coil expands and it literally pulls the breaker open, and that interrupts the electricity and everything cools down, and it prevents your conductors from burning up. And so if your conductors are rated for a higher amperage than what the breaker is rated for, then even if you had a ground fault occurring through those conductors, if the ground fault current is less than what the conductors are rated for, the breaker opens and the conductors stop and the conductors don't burn up. That doesn't mean that when the ground fault was occurring that there's not some dangerous electricity flow from, where it's supposed to be down to where it's not supposed to be. But the plan with, a breaker is to interrupt that flow without causing a fire. So to interrupt that flow without the conductors getting too hot. Um, okay, but what about, say, an arc fault, where it's in line, but it's not as powerful as the entire appliance, defaulting to ground, where you just have a little light contact. Um, there's, if you had a minor arc fault, what if the device that was ground faulting had two different power settings, one at full power and one at 1/3 power, and it was only ground faulting at 1/3 power, and that would be not enough to open up the breaker, uh, but it might not be enough to burn up any cables or cause any other errors, but it would still be occurring. So how do you detect these smaller than what the breaker is rated for faults? In fact, there is a sensing coil inside your ground fault detection circuits. These are the circuits that have the little trigger that you have to press on them. And what they work just like an electrician's clamp meter, where they clamp around a wire and they can measure the current that comes through it. The ground fault detection breakers are monitoring the return path of the electricity, which is the neutral. And if there is excess current in that neutral that still can be less than the breaker rating, a ground fault circuit will detect that and then interrupt it. So only these ground fault circuit interrupting circuits can detect current that is faulting to ground that is less than the size of the main breaker rating. And so I guess one point is you could still have a ground fault without tripping your main breaker. And that is where you get into ground fault detection mandates in particular pieces of equipment. Okay, so some other common definitions listed, which is evaluated and published by an organization acceptable to the AHJ. So some local jurisdictions will say only UL listed, and if you want to use another listed agency, you just talk to the inspector ahead of time rather than surprise them at site. But there's no real reason why an inspector wouldn't accept non-UL listings on US sites. Let's see, within sight or visible is restricted to 50 feet. And so sometimes with these disconnect requirements, you get the buildings spaced further apart, like solar array on a barn going back to a house. That visibility requirement is really there so that it's not over a long distance. Even if it's visible over a long distance, there's a limit to your visibility. One way to think of it is that if someone was 20/50, you would not very good vision at 20/50, but they could still see that disconnect switch no more than 50 feet away. Let's see, NEC 2020 defined island mode. Anti-islanding is a term that is a little bit confusing, but basically a microgrid is an island, and then your grid tied, that's the regular mode, the non-island mode. And there's some advanced issues on that, of course. That relates to inverter interactive system. So an inverter interactive system is intended to operate in parallel with the electric utility. And if I'm a non-electrical engineer, I think parallel lines. And so I think, okay, well, you have one grid operating forever in equal distant next to something else, but never touching or intersecting. That's the opposite. This is like parallel electricity, like series versus parallel. All of the breakers on your service panel are wired in parallel. And so when you look at a parallel inverter system, that's an inverter that's plugged into a breaker that's connected to the electric grid. The grid in this case is playing jump rope, and your inverter has to jump in and synchronize to the grid. So parallel inverters have to be synchronous, they have to mimic the grid, and they can't generate their own grid form. And so that gets into the bidirectionality of charging versus charging in parallel or not in parallel and out of sync. All of these terms, are precisely referred to in National Electric Code. A damp is moderate wetness. Wet locations can apply to slabs. Oh, hold on, I never shared this poll, so there we go. I'm gonna hide it again, in the interest of time. Let's see. So a raceway is an enclosed channel designed for holding wires, cables, or bus bars. So enclosed is standoff, but okay. But if I have like a metal piece of unistrut that is open on one side, what is the definite or a cage of wires versus a fully enclosed conduit? A raceway is regardless of whether it's conduit or specialty cable, it refers to that enclosure, whether it's fully enclosed or partially enclosed. That the way the cable is making it back from start to finish is going through a raceway if it has any kind of enclosure at all. So some cables will be rated for use outside of conduit or outside of a raceway even. Depending on how strong they are. Sealable equipment, a means of sealing or locking so that live parts cannot be made accessible without opening the enclosure. That's not the same as sealing your equipment, which we'll get to a little bit later. This is not just a dry repetition of code. This one stuck out to me as there's even a definition for reconditioned, and says if it's rebuilt or refurbished or remanufactured. So they're in certain parts they'll, I don't know, maybe restrict you to harsher requirements for reconditioned equipment. And this doesn't have to do with electric code, but on the side, the IRS tax code for the commercial solar tax credit, it even allows you to use used or refurbished equipment so long that that material does not comprise more than 20% of the total system cost, which is interesting because now there is a market for refurbished or used or reconditioned lithium-ion batteries. And so there might, in the battery section, there might be harsher requirements. And we got, other codes, the tax code referencing, overlapping material. Another challenging definition is separately derived. An electrical source having no direct connection to the circuit conductors of any other electrical source other than those established by grounding or bonding. We're going to talk more about that in a minute when we get to the grounding and bonding sections. Let's see. Some general definitions. This is a change to electric code, which it says that 110.14 is the bottom ones that I'm talking about. The installation terminal connection torque. It says an approved means shall be used to achieve the indicated torque value. And so every terminal, every connection on your electrical equipment comes with a torque value in the installation manual. Torque this connection to that much. And an electrician can easily say, well, I do this every single day, so I know what the connections should be tightened to. And then their journeyman says, you got it, I know what to do, I'll take over. And then the helper does the actual connection with a power tool and it never gets checked. And where you start to have problems in your electrical connections are loose connections primarily, but there is such a thing as over torquing and cracking the breaker or the shell of whatever you're trying to mount to. And so, at the bare minimum now, code is mandating the use of a torque wrench for every connection. And so where installers who are abiding by this do it is, they'll just have some guy with a torque wrench come through, afterwards to make sure that all the connections are torqued to spec. So in the solar industry, you might mount the array, and then as you go, a guy follows it up with a torque wrench to make sure every piece was tightened to the right value. Of course, that doesn't really prevent over tightening. All right, electrical spacing. So still in the first 100 section, the spacing around the equipment cannot be shared with any other spacing. So it has to be dedicated. So it may look like this room is a mess, but actually, if you can draw a rectangle around your dedicated electrical space, it only requires 6.5 feet from the ground. And so that air conditioning duct is actually outside the 6.5 foot height requirement. And so even though it's above the electrical equipment, it has enough clearance to be fine. Similarly with that hot water tank, that has some plumbing. It looks like there's a gas line, but it's still kind of off to the left. And I guess we're assuming that all that security stuff is low voltage. Really the only code violation that the inspector will have the most problem with is the storage stuff in front of the service panel. So that's when we talk about dedicated spacing, as it's not just within the keeping gas out of electrical or plumbing out of electrical. It's also dedicated where you can't have other stuff being stored there. Locations. This comes into a big in the solar industry because we install on the rooftop, which is not just a wet location, it's also a hot location. And so the boxes that you buy, your terminals that you buy in the solar industry are rated for a hotter environmental rating than the standard stuff you get at the store. And so if you're doing all your temperature calculations at the hotter temperature rating, and then you're running out to Home Depot and you're buying the stuff at the lower temperature rating, you can run into a design error that way. So generally, the equipment that you're using on the rooftop is going to be specialty equipment. Once you get inside the attic, you're now in a wet and dry environment. If you're in AC wiring, you don't even need metal protection. You can just be in Romex. DC requires metal protection. A basement is considered a damp location, and the concrete slab on the bottom can be considered a wet location due to the conductive nature of concrete. So we'll get into that. The main error that I see with locations is that solar installers use a lot of metal EMT conduit, and that's because it's good physical protection and it's commonplace. And if you go into the building, you need to be in metal. The problem is the box stores like Home Depot, they don't sell the rain tight EMT connectors. And so, that sometimes can be a special order item. But essentially, every generic piece has a term, and you can get a rain tight 1-inch EMT connector, or you can get a standard 1-inch EMT connector, which is not rain tight. So you have to be looking at your components to say, is this a wet rated component or just a dry component? Is this component rated for higher temperature or lower temperature? That is this rated for inside of conduit, or can it be rated for outside of conduit? All of that is driven by your location. Rather than memorize the spacing requirements, I think about them like, what could one person stand in front of and comfortably work without hazard in this area? So comfortably stand, that means a 4-foot room, a little tunnel underneath the side of a building foundation is not an appropriate work spot for, electrical equipment. You need to be able to stand in front of it. The minimum width, the side to side, is only 30 inches, so about the width of what one person can work in comfortably. So that's not really the hard thing. Dedicated 6.5 feet, the doorway, like we talked about before. The depth is the one thing people get caught on. Is in this picture, there's an error, because to access the service panel, you would have to lean over the battery bank. In fact, that's a code violation. If you look to the left, there's panels that are, maybe 4 inches deep, and another panel that's 6 inches deep. The code says, within that same vertical space, from one equipment to the next, if they're sharing the same vertical space, they have to have a depth that is uniform within 6 inches. No leaning over electrical equipment to work on other electrical equipment. There's a rule for whatever is behind you as well. And I'm not for memorizing all the numbers and tables, although they do show up on electrical exams. So what I think about is, the range is 3 to 5 feet, and there's less of an allowance for lower voltage systems. Once you get into higher voltage systems, you're up at the maximum allowance. And then on top of that, it depends on what's behind you. Is there electrical equipment behind you? Or is there a wall behind you? Or is there nothing behind you? It's like, well, that's weird. Why do I need to have dedicated space if there's nothing behind me? You can't put storage in that space. So if there's nothing behind you, you're dealing with a 3-foot requirement. But if there's something behind you, if there's a wall behind you, you need some additional footage. And then if there's electrical equipment behind you, you need even additional footage than that. And if there's high voltage electrical equipment behind you, you need even additional footage than that. And that range is between 3 feet and 5 feet. And so, if you're planning your batteries, and if you're using batteries that need maintenance, what that means is at minimum, if there's nothing else around, you need a 3-foot walkway on all sides of those batteries. And if there is electrical equipment around, depending on the voltage of that battery bank, you're looking at a 4-foot walkway, or if it's a high voltage battery bank, you might be looking at a 5-foot walkway all the way around the battery shelf. Let's see. So dedicated equipment space. If there are exposed parts, like you're building your own battery case, that area needs to be locked so that service personnel only enter it. So that gets into maybe shared spaces not being particularly good. If you're putting your batteries in a service closet that shares it with storage and the water softener and all that, then you might need to put an additional cage around your exposed batteries. And in the other aspect is for guarding of live parts is to prevent physical damage. And so that's another aspect of, well, when do you need metal conduit versus non-metal? That metal conduit there is to prevent physical damage. And so, if you're running power lines along a driveway versus up on a rooftop, there's a different, requirement for physical protection. So you might not need to be in conduit, up on the rooftop, but then you're right down on the driveway. Now it's mandatory because of physical protection. Okay, so we're getting to polling question 3, and then right after this, we're going to take our 10-minute break. So I'm going to launch polling question 3, and you can vote on it and go into the break. So what is not a general rule for electrical equipment? So try and find the one item on this list that doesn't sound right to you, and sure enough, that one item on the list will be a electrical code violation. So go ahead and vote. Then we're going to take a 10-minute break, and we'll be right back at 1:10. All right, everyone. Welcome back. So the space in front of your service equipment cannot be used as storage. That's not the general rule. So all these other things, I guess it's a little awkward wording. Anyway, that's the poll question. So let's move on. Now we're really gonna have to start picking up the pace. Article 200. So now or really chapter 200 is getting into the power supply issue. So we're going to start out with a definition of a grounded system. It's connected to ground. The alternate is an ungrounded system. It's an advanced issue, but it has to do with how you can have a reference voltage potential rather than establishing the negative to ground or the positive to ground. And there's different ground fault detection requirements and positives and negatives for both. So generally speaking, there's this newer kind of grounding methodology called floating on the DC side, which is to not ground either side, but to put overcurrent protection on both ends. Undergrounded conductors shall not be tapped from grounded systems. So we talked about earlier about how loads could not share the same as supplies. We can apply that knowledge to say, okay, well, if I have an air conditioning unit, power supply coming to that, could I interconnect my solar array right where that power comes out of the building for my 240 volt air conditioner? So I have a 240 volt air conditioner, I have a 240 volt solar array. Can they share that same line? And the answer is yes. In fact, you could put a little sub panel there instead of that disconnect switch and tie the solar array in at that point. If that circuit between the air conditioner and the service panel is dedicated. If there's no other load on that circuit, right now it's a feeder, it's a branch circuit for the air conditioner unit. If you intercept it, put a power distribution panel there, it's now a feeder from the distribution panel to the main panel, and then your solar array plugs into the panel and your air conditioner unit plugs into the panel. So I think this is one of the more cost effective, if you're trying to go for a very low budget do it yourself project, putting a 100 amp service panel and putting a 60 amp breaker on it or whatever your air conditioner unit is, that can be a good spot to interconnect a solar array. Identification. So cables over number 4 gauge or greater can be colored with tape or tagging or approved means. Anything smaller than number 4, so this includes number 6 and down, should be colored wiring rather than taped wiring. So this is a big issue in the solar industry because we're so used to just using number 10 spools of black solar cable and taping it positive and taping it negative. Then you'll see the most professional crews using colored spools for their positive and negative side. And the answer is, well, which is correct? And in fact, National Electric Code says those circuit conductors up on your solar array, up on your rooftop, need to be in colored cable, number 6, red for positive, black for negative. And that's not in, section 690, that's in Article 210. So let's just do a very quick poll, guys. Let's try and get this one done in under a minute. So let's get up to 90% participation. For those, if you're familiar with solar cables, are you using colored solar cable, or are you lacking experience? Let's see, we're at 45% and climbing, so we need people to come in and vote. And we have some people saying I've only used black solar cable. I've been using all black solar cable up until this year. But it really doesn't matter because regardless, it's going to be the solar cable's a specialty cable. It's like high voltage, for it can be rated up to 2,000 volts. It's rated for outside of conduit, so its cable jacket is super thick because of voltage and because of its exterior environmental rating. Almost done. So just in the interest of time, we're going to close and share. And so we see, as many participants are using black only solar cable rather than colored solar cable. Now you can tell the project that you got to get spools of red and black to be code compliant. All right, moving on. So Article 200, services, feeders, branch circuits. It says load unevenly proportioned amongst branch circuits. Where I have found this balanced load issue to be coming back nowadays is with LED lights, where if you have what this means is there's a like in your standard 120 240 electrical service, we say there's two 120 volt legs. They're equally out of phase with each other. It's not really a positive and negative like you have on DC, but it's perfectly out of sync phases alternating between positive and negative, like mirror images of each other. They all connect to that common grounded neutral point. Both of them have their electrical voltages to ground. And if you get more load on one end than the other, that return current can recirculate and cause some power quality issues. And so if you have flickering LED light bulbs, in this happens with high-end solar components and batteries as well as low end. You may want to check to see if you have the same amount of load occurring on both phases. Relocating a breaker from one side to the other can reduce that issue. Minimum ampacity side, so not less than the load served, and then rated for the continuous load plus 125% of the non-continuous load plus 125% of the continuous load. So we see an additional 25% ampacity being required on loads that are always on for 3 hours or more. So what that's saying is, I know that load is going to be always on. And so I know those conductors are going to be running at a higher temperature than if those conductors were not subject to a load that was always on. And so if it's a non-continuous load, you got to rate it to the amperage of the load. But if it's a continuous load, if it's always going to be on for 3 hours straight or more, you got to give it an additional 25%. And that additional 25% it reappears over and over and over again. I call it the standard 25% upsizing. It says take the load of the circuit, upsize by 25%, and that's going to be your conductor size. So if you're asked to do ampacity or voltage calculations on an exam, and someone's holding a gun to your head and saying you need to upsize your wires, by how much should you upsize, and you don't know the application, you have to take a random guess. This is purely a hypothetical, not something you do on a project, but most likely that upsize is going to be 25%, unless there are special conditions that would say you need to upsize it even more than 25%, which once you get into like the solar, it's like, well, solar is on for 3 hours or more, and it's a continuous load, so you need to upsize by 25%. But then beyond that, you get into different performances at cold temperatures versus hot temperatures, and that allows for additional ampacity allowances of another 25% under certain uncontrolled natural cases. So by and large, you get the ampacity of a circuit and then you upsize by 25%, and that's the rating of the circuit. That means you'll have all these 20 amp breakers, and they should only have 15 amp loads on them, 16 amp loads on them. So on a microinverter circuit, if it's limited to a 20 amp branch circuit and each microinverter is 16 amps each, you go up to 16 amps, and then you add on your additional 25% over current allowance, and then you put it on a 20 amp branch circuit. If you put 20 amps of load on a 20 amp breaker, you'd be tripping your breaker all the time, because it would run up to that 20 amps and then heat up the wire to where it should be at 20 amps and then pull open the breaker. That does in fact mean that you can run at a higher amperage than what the breaker is rated for a brief period of time before it trips, such as a surge load that might only last for a minute. So think about loads in terms of which loads are continuous versus non-continuous. And it can also come down to, is the load, maybe a dishwasher is a non-continuous load, but if it shares a circuit with other appliances, it turns into a continuous load for that circuit rating. Air conditioners, refrigerators, even solar arrays would be treated as continuous loads. Okay, so let's get into the next polling question. So let's try and get this one under a minute. And so it's, does your home have a power outlet on the front and backyard? And so we need few more people to answer. We're almost done with this one. That's pretty good. So let me go ahead and close that and share it. Now we say most people do, some don't, and some say I don't live in a 1 or 2 family dwelling, like an apartment complex or a quadplex. And so it says, in fact, 1 or 2 family dwellings are mandated to have a readily accessible plug at the front and back of the dwelling. So now we know readily accessible means someone should be able to walk up to it without a ladder to access. And there's pretty strict requirements on, this is what electric code guidelines. There's no point along the wall space more than 6 feet from an outlet. And what that is trying to say is we don't want people running extension cords throughout their house in order to use their devices. So code can seem stringent, but it's there for a reason. So now we get into the sizing of our feeders, and we have minimum feeders for under 600 volts is you rate to the continuous load plus 125% of the continuous load. There's an exception that says, well, if your whole assembly is rated for 100% of the load, your feeder needs to be able to supply 100% of the load. So sometimes you'll have additional fuses or protections that will blow or stop the circuit from functioning when it reaches past that 100%. And then it's, you follow the manufacturer's instructions. Feeders with a neutral, the neutral needs to be run in the same raceway as the conductors. circuits derived from auto transformers need to be connected to the grounded conductor of the system. We're going to talk about that in a minute. Identification of feeders. So when the premise wiring has feeders from more than one nominal voltage, each ungrounded conductor shall be identified by phasor, line, and system at all termination, connection, and splice points. That's saying that your conductors need to indicate, that they're positive and negative and at what voltage. Basically these become sticker requirements in the solar specific questions. We have different, our buildings run at different voltages based on the utility transformers behind them. And what that means is you need to match your equipment for those specific transformers. 12240 is pretty common on residential. I guess some inverters run at 120 volts, and you have to match them up to make a 12240 connection. But you need to match your electrical service. Here's one I liked as an engineer talking about significant figures. Fractions of an amp are rounded to the nearest whole amp. So we don't need to put in, deal with 9.1 amps. That's just considered 9 amps. You can round your calculations. Okay, so we talked about our load tables. These are what they look like. They vary by function, they vary by size, and there are discount factors for the larger the building gets. And so, if everyone in the hotel turns on their air conditioner at the exact same time, you might end up tripping the main breaker for the entire building. Because they've assumed that that isn't going to happen. I mean, say for hotels, once the load calculations start to get above 100 kilowatts, you can start discounting that load by 70%. And so the lighting loads have been substantially reduced for NEC 2020. And then here's another one. It says you can calculate units provided certain conditions are met. Automatic means to take action and reduce the connected loads shall be permitted. If you're looking at calculating a continuous load with your engineering calculation, you still add an additional 25% to that. So what that means is now with batteries and smart digital controls, we're getting more advanced at being able to kill certain loads when other loads click on. And National Electric Code, by and large, allows engineers to step in and say, hey, if I'm designing this system and I'm stamping it to say, we have a battery and load management system that will limit the power draw of the building to this amount, that can override the tables and charts so long that you're an engineer making that calculation. And that's important because the higher your amperage is, voltage is not so costly to go from 300 volts to 600 volts or 600 volts to 1,000 volts. You're buying a little bit thicker plastic on your cables. The amperage, when you're going from 200 amps to 400 amps or 400 amps to 800 amps or 1,600 amps or beyond, you're doubling your cost, you're doubling your metal, and then some, because the market shrinks too, so there's less product availability. So when you're doubling your amperage, sometimes you're more than doubling your cost. Non-coincident loads, so electric code is saying, well, look, if these loads are going to be on at different times, it's possible to use the largest load of the two. For air conditioning loads, they'll look at running your AC to the maximum, running your heater to the maximum, or running a combination of air conditioning and heat to see what the maximum load condition is. And then we get to the neutral load calculation, and at sometimes the neutral is allowed to be undersized or eliminated entirely. Neutral loads are a kind of the hinge of a seesaw. They're what allows your imbalance between your electric loads from one phase to another to kind of drain without causing power quality issues. 240 volt devices that don't have any other loads on them are perfectly balanced. And so 240 volt devices like some air conditioning units don't even need a neutral. And so based on what the exact application is, you can eliminate the neutral entirely for 240 volt devices. And then sometimes you're allowed to undersize it. And so, while we don't have too much time to go into different types of electric services, that transformer that hangs on the side of the building is literally wound with copper wire in certain ways to convert voltages. This is the real reason why we have an AC electric grid. It's because AC is easier to convert, to step up and step down into different voltages with transformers, so that we take a high voltage grid and drop it down to a low voltage service. A volt times an amp equals a volt times an amp. If you have high voltage and low amperage and you step it down into low voltage, you can get high amperage out of that. And so we step up the voltage to transport electricity on over very long distances, because by and large, voltage is cheap and amperage is expensive. That the thickness of your metal wire is more related to amperage. The cable jacket is more related to voltage capacity. The power lines might not even have a cable jacket. They just space them out so that the air is the insulation. Let's see, I guess where this was useful is recently I was rewiring a hot tub, and it was on a 240 volt circuit. And is it 120 240, or is it 240 from 0 to ground? If it had a neutral, well, in this case it was two 120 volt lines and a ground, rather than a 240 neutral and ground. At the commercial level, you talk about delta versus Y electrical systems, and that has to do with the transformer wiring. And then all of your battery inverters and motors and equipment have to match the electrical service that you're powering. In the interest of time, I'm going to kind of skip over some of these load factors. Basically, if you have an existing load, you're allowed to use your maximum load over a 1-year period, which is probably not, if you have more than 1 year of demand data, then that's probably best. Clearances for overhead conductors, 15 feet for over 300 volts, 18 feet or more for driveways. Above rooftops, an 8.5 foot clearing. Except for when the roof is subject to final pedestrian traffic, where you get back to the above section. So when you're trying to design a covered rooftop deck with solar, what your code is saying is that, those wires, first off, you might not want to use the traditional 600 volt solar design format. You might want to use a 300 volt format to get you a little bit of a lower, patio covering or pergola, but it still needs to be 15 feet up in the air. If you want to get people walking underneath those power lines. Raceways need to be approved to drain. So sometimes, when I first got into electrical, I'd look at power lines forming drip loops before they go into the house. And I'd say, man, why do they make it look so ratty having these power lines just make these droops before going in? Well, it's so that the rainwater will fall down the line and drip off the conductors. And that applies to not just, the power lines going into your building, but, solar conductors coming off the array and into the box before they go down into the roof, or solar conductors coming down the wall before they go into the next piece of equipment. Raceways on exterior surfaces need to be arranged to drain. That means making a weird loop going, into the underside of the equipment rather than into the top or into the side is often the only manufacturer supported way of entering equipment on exterior surfaces. So sometimes aesthetics can get in the way of, you try and make something look good. If you aren't arranging it to drain, you can get water into the box, and the good looks are not as important as safety in this issue. Vegetation support. Electric code has come on to say, no, you can't just use regular trees as support for your power lines or crazy solar arrays. This is a good one, the Raceway seal. So when you're entering a building from the outside, you have to seal the inside of the conduit, because the air between the inside and the outside has a temperature differential, and that can cause condensation and moisture inside of your conduit. And that's true from any temperature differential. So that's true from underground to above ground. It's also true from going from the top of the roof into the building. And so some solar installers will open up a box and they'll see a puddle of water at the bottom of the box, or even worse, I guess I didn't share it, so I'm getting through that. Or even worse, they'll open up the box in the wintertime and it'll be full of ice. And where is this water coming from? It could come from rain, sliding down the conduit into the box. It could also come from the inside of the box itself if you're allowing that airflow from the colder temperature to the hotter temperature to go through. So raceway seals are a common electrical exam question and a common kind of oversight from an installer. Anywhere where you're going from the inside to the outside, from one cold temperature to one hot temperature, the inside of that raceway needs to be sealed. Power supplies. So you're only allowed to have one power supply going into the building unless it's a special circumstance. And on-site power production systems are one of those special circumstances. So there's actually a lot more design flexibility with adding solar and batteries than people think. So let's see. Let's go into our next poll question. So what is the difference between a main lug only and a main breaker panel? Well, we haven't answered this one yet, so just guess. This is just a participation. This is not for a grade or anything like that. But go ahead and get your vote in. So what's the difference between a main lug only panel or a main breaker panel? The main breaker has that main switch up at the top of it. Main lug doesn't have that switch. The conductors just come in and land on the top. They're a little bit cheaper because you're not buying that 200 amp breaker, that main switch that's up at the top of it. So when can you avoid that cost and not get the main lug only panel versus when do you need to buy the one with the switch itself? So we have a couple of different questions here. I'm going to close it. Now I'm going to share it. And so what we have is the answer is panels with more than 6 breakers need a main disconnect switch. So that is the rule. It's called the 6-handle rule. And it says once you count up all these breakers that you're trying to turn off to power down the whole building or whatever is powering this panel, once you get more than 6 switches, then you need to have a main breaker. And so these main lug only panels are generally smaller with fewer breaker slots because there's only so much you can fit on them before you would need a main breaker switch. Or you might have, a external disconnect switch, like a knife switch disconnect. And so if you're already using the knife switch disconnect, then you may say, well, I don't need that main breaker up top because I already have the main disconnect switch right next to the equipment. So, adding yet another disconnect switch would be redundant. Or you could get into that the inspector wants a knife switch on the outside of the wall, but you'd still have your main breaker on top of your main service panel inside the wall, and eliminate the confusion over the additional exterior disconnect, or what this rule is. But essentially, if you have 6 switches and you need to more than that, if you want to power down something that you're immediately around, no more than throwing 6 switches. So if you have a 800 service panel and you have 6 100 amp services coming off of it, they don't need to be wired together to be one master disconnect switch. But if you had more than that, then you would need a main disconnect switch for it. Now the thing is, every special group, so your backup systems, your fire alarm systems, those are considered separate supplies, or can be considered separate supplies. And so you can apply this rule within groupings, but it's wherever there's one group of similar disconnect switches. If there's more than 6 of them into a panel, you need to have one switch you can throw to power them all down. The type of disconnect switch can be all over the place. You don't always need a knife switch. A knife switch disconnect and a breaker are both disconnect switches. We have a call out for identifying whatever feeders are supplying a panel. And so it's not, solar discrimination to say you have a solar array, you need a 1-line diagram that shows how the power enters the building. When you have a combination of feeders, a directory explaining where they're going is required. Disconnect switches need to be manual. If they're powered, there needs to be also a manual option. We get into simultaneous opening of ungrounded conductors. So it's not a disconnect switch for each pole. It's a double pole disconnect switch where the one switch disconnects both poles. In the boat marina industry, you might get single pole battery disconnect switches for turning the battery off so the battery doesn't drain when you're not using the boat. That's not the same disconnect switch that you can use for disconnecting these power feeders. Plainly indicating whether open or closed. So then we get into some switch specific requirements, like isolating switches that say for over 1,000 volts, the switch needs to have a visible disconnect, which means that you can look inside of it and actually see where the disconnecting point is made. So a breaker, you can't see inside a breaker. That's not a visible break. It doesn't mean a viewable break. They make these switches with a little plastic window so you can look inside and see it working without taking the cover off. A visible break means you can take the cover off and look inside and see the disconnect being made. And then once you get over 1,000 volts, they say up indicates on, unless it's a 3-way switch where the middle position is off. but up is always going to be on. Up is always going to be the grid side of things. Up is going to be energized, where down or the middle position is off. Service entrance conductors were subject to physical damage. They say you need to beef up your protection. So this is where it says if your service entrance conductors are subject to physical protection, you need to put them in, Schedule 80 PVC or EMT, commonly rigid. Everything's governed by code. The clearance requirements, the distance between supports. Well, here's those drip loops we were talking about. So when you get to breaker sizing, the main thing is you calculate your overcurrent. So you have 16 amps of load on a circuit, and you add 25%, and that's 20. That's 19.8 amps. And you say, well, what do I do? If your calculations are 800 amps or less, then you take your load and you take your conductor sizing, and then you round up to the nearest breaker. So if I have a 16 amp load and that comes out to be 19 amps with my overcurrent calculation, I put it on a 20 amp breaker. And so it's like, well, what does that mean? It's like, well, if I get 19 amp cable and I put it on a 20 amp breaker, couldn't I have one extra amp and burn up my cable, but the breaker doesn't trip? Well, in reality, we don't get that granular. So you're probably going to be looking for 19 amp cable, but only be able to find 20 amp cable. So, what happens is when you get over, 800 amps, your fuse breaker sizing stops being so granular. You don't get such resolution. And so, that problem only becomes an issue when you get over 800 amps. So, basically when you're making your calculations for under 800 amps, you're calculating your load, you're applying your what is usually a 25% oversizing correction, and then you're rounding up to the nearest breaker size. Whereas if you do that 25% oversizing correction and you get to like 404 amps, then if you have I'm just making up some numbers here, but let's say you have a 250 amp, or let's actually be correct. Let's say you have a 650 amp device, and then you apply additional 25%, and that gets you up to 810 amps. You would then put it on an 800 amp breaker, but you would get your conductors to still be rated for a minimum of 810 amps. So that's just kind of the weird thing. It's when you're over 800 amps, you're rounding down the breaker size. When you're less than 800 amps, you're rounding up the breaker size after you've done your ampacity calculation. Ungrounded conductors need to have an overcurrent protection on each conductor. Let's see, conductors have these things called taps, and it says if each, you're committed to tap onto your feeder. And if you tap onto your feeder right around where the feeder comes into the building within 10 feet of that, if all the taps going in are within 10 feet, then you don't need to have additional overcurrent protection. But generally speaking, when you're tapping wires together, so if you have the grid coming into the building and you say, I want to intercept those wires and tap new wires onto them, establish a new service for my solar array. When you have 3 or more wires together, at some point in that connection, whether it's over at the service panel or right at the tap itself, you're going to have overcurrent protection, like a breaker or a fuse. In the interest of time, we're gonna skip over polling the next polling questions, but we say a solar installer installs a sub panel and connects the neutral to ground at the panel. What is the safety hazard? So this is stated a little bit differently in the next slide, where we have a panel and a sub panel coming off of it. And it gets into a neutral to ground connection that is that gets confusing if you don't know what the neutral to ground connection does. Your ground is 0 volts, and your neutral should be 0 volts. And to make that neutral 0 volts, we connect it directly to ground. But the difference between having multiple neutral to ground connections and only one where it's supposed to be is the difference between a water balloon with the water coming out the neck of the balloon, or a water balloon that's full of holes and water is just spilling out everywhere and maybe the balloon will pop. For our ground fault detection currents circuits to work, we need any ground fault traveling all the way through, where the ground fault is supposed to go, all the way through the grounding system and out to ground in one spot. And if it doesn't do that, then we can't detect ground faults as easy. And so if there's a ground fault, we want that current to be carried back through the system and to be able to detect that that unutilized current is sensed within the neutral, or at least the difference between what's faulting to ground and what's being returned through the neutral we can measure. If that return through the neutral doesn't make it all the way back to the service panel, our ground fault detection circuits can't work. They can't monitor where that electricity went. And so particularly with those faults that are less than the main breaker rating, if we can't monitor and track that, then those ground fault detection circuits don't work. And so the only way that ground fault detection circuits work is if there's only one location on a service panel where the neutral's connected to ground. If you just said, oh, my neutral's connected to ground, and so anywhere in the system I can connect my neutral to ground, we would miss the difference between the current that's faulting to ground and the current that's being consumed. We wouldn't be able to measure that in any known way. And so the danger is when you're designing these systems, code will tell you you need to make a main bonding jumper. You need to connect the neutral to ground. And the danger is you need to stop and say, okay, well, on this electric service that I'm adding to, there is already somewhere on site a neutral to ground connection. And so if I'm joining up to an existing electric service, I do not want to create a new neutral to ground connection. I'm going to use the one that's already been made as my one neutral to ground connection. If you're establishing a brand new service, if you're tapping on a brand new service up at the front of the building, then you may make multiple neutral to ground connections. If the fire alarm system is other than the utility feeders, if the fire alarm system is completely removed and detached on its own electrical system than the rest of the building, then the fire alarm and the rest of the building may have their own unique neutral to ground connections within those main service panels. But beyond the main service panel, when we're talking about sub panels, inverters connected to the load side of an existing electric service, you don't create a neutral to ground connection, even if code tells you to, because there's one already existing. So this is the biggest kind of safety mistake that an amateur or beginning solar installer can make is they install the solar disconnect switches. It says you need to have a main bonding jumper connecting to neutral to ground, You need to take a step back and say, well, wait a minute, does one already exist there or not? So they say that neutral to ground connection is called the main bonding jumper. So here's another kind of side note. Parallel conductors in 2 or more raceways should not be smaller than 1/aught cable. So this is a different instance, but cable is rated for so many amperages, 20 amps, 40 amps, 60 amps. Once you start getting into utility conductors, they start getting thicker and higher amperage. At some point, you may say, well, is it easier to buy and pull and install 2 smaller wires than 1 big, thicker wire? And often that's not really how the decision's being made. It's more like we're installing as many big, thick wires as we possibly can to meet the application. But the code says, when can you go down and do 2 parallel runs instead of 1 larger run? The parallel runs of the same circuit for additional power ampacity are only allowed in wires that are 1/aught or larger, which is pretty thick wire. It's just 1 step down or 2 steps down from your welder's battery cable. When I open up electronics, I see parallel runs being made with wire that's less than 1/aught, but that's a listed UL assembled, manufactured assembled product that is using that parallel run behind the scenes. The difference is this is a parallel run that an installer is making out in the field as part of their kind of field designed and installed system. So parallel runs are only allowed for cables that are 1/aught or larger. Says where a main bonding jumper and a system bonding jumper is a screw only, the screw shall be identified with a green finish and be visible when installed. So often these sub panels will come with a screw that you can put into them that will connect the neutral to ground right at the panel itself. And so you may get a panel delivered to you and it may have a green grounding screw. And the difference is, is it the main panel? Is there already a neutral to ground connection being made ahead of the green panel, like in a external disconnect switch or the utility meter itself? So don't just willy-nilly screw in the green screw and ground the service panel because it's there. You have to ask, am I building a brand new service and I need to establish that neutral to ground connection at one spot, or has it already been done for me? The grounding electrode conductor, and I think at this point, in the interest of time, we're just going to do some gotchas in the chart, and that's it, because we're coming up on the 2-hour mark. The main thing is rebar in concrete. You have to have 20 feet of continuous rebar for that rebar to be the ground electrode. These ground rods are, 8 feet, 10 feet long. 8 feet needs to be in the ground. So that's a lot of copper in the ground. There's some alternate ways to make the grounding connection, such as circling the building in smaller concrete. But basically, if you use a ground rod, you get a lot more flexibility in this cable coming off the ground rod. Anything that's like you making something in lieu of using a ground rod is going to require more copper. You can buy a testing device to test your resistance to ground. In dry soils and in rocky soils, putting in an additional ground rod is not a bad idea. The ground rods have to be spaced 6 feet apart to function. And now we're coming up kind of towards the end of the program, and we haven't made it into section 300 yet. So just some common gotchas, and then we'll end. the ground path between metal conduit and your electrical box, you get these rings that are called concentric, where there's an internal knockout and an external knockout. It's only considered grounded if you use the external knockout. If you use the internal knockout, it's an impaired connection. And so you gotta use an additional ground wire that comes off of the connection and carries through the rest of the system if you're using those impaired connection holes. So sometimes you'll see these knockouts and these lock rings with a grounded wire attached or one that's not attached. And it depends on not even just if you're using a metal box, but what knockout position you're using within that metal box. Your ground electrode conductor has to be marked green, unless if it's number 4 or larger, it could be taped green. So we start to see the electric code requirements begin to repeat themselves as we go through. If you're coming into the next month's webinar, we're going to start with the battery and solar section. So what we really kind of didn't really get to today is the Article 300 wiring section. The main thing that we aren't going to have time to cover is the temperature correction chart, which is if you're using cables that are rated for a lower temperature, but you're using them in a higher temperature environment, how do you derate them to make sure you don't burn your conductors up? And the derating factors can be rather substantial, 60%, 40%. The last thing that I want to show you is this chart, which is there's a section in the middle of code in the 300 wiring section that goes through all the cable jackets. And the short of it is, there are wet condition cables, dry condition cables. There's the -2 is for environmental exposure rating for sunlight versus not. The cable jackets and the letters stand for different things. And, basically it's wet versus dry, high temperature versus low temperature. And ultimately that traces back to the cable jacket itself, how thick it is, how robust it is. And by the time you get into solar cable, you're at high voltage, outdoor, environmental rated, wet rated, and its jacket is 5 times as thick as the jacket you get in a coaxial cable for your television antenna. So, just use the handouts as additional references. If you have additional questions or code-specific questions, let me know. We might cover some of this and at the end of next week's webinar if we don't get to it, but out of respect for your time, I'm going to pass it back to Red Vector.
Thank you, John. We greatly appreciate your time and expertise. So let me go ahead and jump here to our contact information. All right, so this is our contact information for anyone who may want to have that. Once again, certificates will be available tomorrow, and we'll notify you by email when you can download them. There'll also be a short survey at the end of this webinar, and we sincerely appreciate your feedback. Now, on behalf of Red Vector and John Ross Cromer, I want to thank everyone for attending. Hope to see you again at a future webinar. Thank you, stay safe, and have a great week.